A quote from Brian Cox. Black holes are a marvelous demonstration of how nature can be both profoundly simple and profoundly beautiful. We are amazed to realize again how little we really know about the universe. Did you still have Hubble, the old space telescope, on your screen? Many people have already forgotten about Hubble or think that the telescope is no longer active. However, Hubble is still scanning the universe every day in search of new phenomena and has now landed a completely unexpected direct hit. Hubble has succeeded in discovering a new type of black hole. These so-called intermediate black holes fill the gap between the known stellar and supermassive black holes. Their existence raises new questions and may now provide us with the key to the formation and evolution of galaxies. Black holes really are a wonderful demonstration of how fascinating nature is. They are so gigantic and mysterious that they are still one of the great mysteries of astrophysics. Until recently, only two types of black holes were known: stellar black holes, which are formed by the collapse of massive stars, and supermassive black holes, which are millions to billions of times heavier than the Sun and are located in the centers of galaxies. The discovery of intermediate black holes shows scientists in an astonishing way that the cosmic landscape is far more complex than we thought. Intermediate black holes have masses that lie between stellar and supermassive black holes. Their existence was proven by precisely analyzing the movements of stars in the star cluster Messier 4. The stars there showed conspicuous movement patterns that can only be explained by the presence of a particularly massive and very compact object. The first indications of this object were found in comparisons of data from the Hubble Space Telescope and the Gaia mission. This object has around 800 solar masses, making it significantly larger than small stellar black holes with around 3 to 20 solar masses, and much smaller than the largest of the dark giants, which have several billion solar masses. The beauty and fascination of these objects lies in their ability to influence and shape the light and matter around them. The beautiful shapes of galaxies and other structures in the universe are probably due to the action of black holes. Now scientists need to clarify what role intermediate black holes play in this cosmic spectacle, and they may be a gateway to understanding how galaxies formed. How are intermediate black holes studied? Have you ever wondered what methods scientists use to study objects that are invisible? Black holes are usually only noticeable because of their behavior. They bend space-time in an extreme way and thus magically attract other objects. The larger the black hole is, the stronger this pull is. If you were to encounter a black hole in space, you could simply see nothing there. Perhaps you would notice a small distortion of stars in the surroundings or in the background. Black holes are most visible when they are in the process of devouring matter. If you were to see matter accumulating in a large circle and becoming increasingly distorted, you might think that a black hole is devouring a meal. Researchers use spectroscopy to determine the radiation of light and gases from stars or other objects orbiting the black giants. Thanks to this method, we know quite well what mass the black holes have and where exactly they are located. Scientists also detect intermediate black holes, or IMBHs for short, using the gravitational lensing effect. When an IMBH passes in front of a distant light source background, its gravity bends the light from these sources, making them appear brighter and distorted. These distortions are perfect for determining the mass and position of an IMBH. These days, researchers are increasingly relying on more and more technological advances. The Hubble Space Telescope has already proven that it can detect and analyze numerous black holes. However, the new James Webb Space Telescope and the Chandra X-ray Observatory are even better. They are playing an increasingly important role in identifying and studying these black giants. Both telescopes offer extremely high resolution and sensitivity, and thus provide even the finest details from the surroundings of IMBHs. ESA has also launched the Gaia mission. This satellite maps the positions and movements of billions of stars in our galaxy with unprecedented precision. This data can help to track the movements of stars in the vicinity of an IMBH and thus measure its gravitational influence. Gaia data will now also help to identify other potential candidates for IMBHs in other galaxies. Theoretical astrophysicists use numerical simulations to reconstruct the dynamics of star clusters and the interactions between stars and IMBHs. The simulations should help to understand the formation and evolution of IMBHs and the circumstances under which they can form. We need such models to put our observational data in the right context and to interpret the role of IMBHs in the cosmic interplay of forces and objects. Studying the motions of stars in dense clusters is another method to study IMBHs. The presence of an IMBH influences the dynamics of the cluster by changing the velocity distribution of the stars. By analyzing these motions, astronomers can again draw important conclusions about the mass and position of the IMBH while observing the interaction of the black holes with their stellar environment. Researchers usually use several of these techniques in combination in order to obtain the most accurate data possible. If the measured values from the different methods match, this is a good indication. Do black holes create galaxies? Since the James Webb Space Telescope was launched, we have been faced with a cosmological puzzle. How could thousands of luminous galaxies already exist at a time that scientists have so far referred to as the Dark Ages? Webb's deep images show us galaxies that existed only 300 million years after the Big Bang. This completely calls into question our previous theories on galaxy evolution, and this is where black holes come into play again. Black holes probably have something to do with the formation of star clusters. Stars are not loosely distributed in the universe. They organize themselves within galaxies, in the center of which there is always a black hole. The beautiful shapes such as spirals, disks, or even vortices are probably caused by the gravitational effect of the black holes in the center. There is always a supermassive black hole at the center of a galaxy. However, how it gets there and when these black holes originally formed is still a mystery. Once we have understood this, we can draw further important conclusions about the evolution of the entire universe. There are sometimes many smaller stellar black holes within galaxies. We have known this for some time. Now the IMBHs are joining them, and it would be interesting to know what a role these medium-sized black holes play and how they are formed. Could they be the merger of smaller stellar black holes, or do they form a category of their own? What is certain so far is that the gravity of IMBHs influences the structure of star clusters and promotes or inhibits star formation in their vicinity. This points to complex interactions, and it almost seems as if black holes are not just all-devouring monsters, but important shaping and regulating structures. Through the use of advanced observational methods, modern telescopes, and theoretical models, we are gaining more and more insight into the true role of these mysterious objects in the universe. Not so long ago, Webb discovered an ultramassive black hole that raises further questions. It existed only 570 million years after the Big Bang and contains 10 million solar masses. This is actually impossible. According to all known cosmological standards, a black hole can never grow to such a size in such a short time. Normally, black holes grow by merging. Many small black holes result in ever larger objects. Of course, the black holes in the centers of galaxies in particular also grow by dissolving matter, but this gain in mass takes billions of years. There is a theory that the first black holes were not formed by supernovae, but are the direct result of the collapse of large dust clouds. The process is basically similar to star formation, except that the rapidly spinning dust cloud does not collapse into a star that undergoes nuclear fusion over millions or billions of years, but into a black hole. Simulations have shown that this is possible. Nevertheless, the size of this black hole remains unusual, as does its age. If black holes existed much earlier than previously assumed, this could rewrite the history of the universe. Sir Roger Penrose publishes a theory in which black holes play an interesting key role. The idea of a cyclical universe roughly envisages that at some point, huge black holes will have absorbed all matter. Then they will evaporate, and finally the universe will collapse. After a state of rest, which takes place outside of time and space, a new universe is created. Black holes, or their final information, could be portals to the rebirth of a complete universe. If this is true, we have so far greatly underestimated the role of these objects. Many questions remain, and we need to advance our science to find out more about black holes. At the end of the day, we still don't know for sure what is going on inside them, and as long as that remains the case, we may not be able to fully unlock the secrets of the universe. Theoretically, there is a point inside where all known forces rise to infinity. That sounds exciting, but this formulation basically just says that our old physics fails here. It's not able to grasp the processes or forces inside the black holes or reproduce them mathematically. Last hope, quantum computers. It sounds too good to be true. Imagine how one technology could solve all our problems. This is exactly what quantum computers could do in a few years or decades, especially if they are combined with artificial intelligence. Once these computing machines are up and running, it will be possible to feed them with all known astronomical and cosmological theories and known observational data. Quantum computers should be so powerful and intelligent that they can show us exactly what we are doing wrong. Quantum computers, combined with AIs, may even be able to unlock all the secrets of the universe and tell us what is going on inside a black hole, how the universe was created, and what its true nature is. At the moment, these computers are still being tested. Quanta store all the information in the universe and exist in several times, dimensions, and states simultaneously. But making them usable in computers still has its pitfalls. Quantum computers get extremely hot and are sensitive to vibrations. Become a subscriber now and look forward to many new, exciting videos.